Hello everyone, today we're going to be talking about thread manufacturing. Let me get my pin going here, there we go. Um, this will be the last manufacturing lecture for this course. There'll be a quiz on it posted on Canvas for those of you taking the course. So threads have been around a long time, starting back to the Archimedes screw and probably before then too. There's been a few attempts at standardizing these things and it's been pretty stable for a while. Unified threads are very common here in the US, and then there's the ISO threads and everywhere else. We use some of the isometric threads here too, though. But pretty well it's the ISO threads and the unified threads. Okay, there's a large number of geometries of threads, but there's only a few that you're actually going to encounter with any regularity. So in the unified thread series, UNC and UNF, the United Coarse and United Fine, those are by far the most common. There's some power drive threads that are a little different we'll talk about, but when it comes to machine threads, UNC and UNF are common here in the US along with the metric ISO threads. And there's some other ones here that I've never heard of or ever seen. Extra fine I've seen, pretty rare. Almost always it's the coarse and fine get most applications. So minor diameter, that's the smallest diameter. Major, that's the largest. Pitch diameter we'll define in a drawing here in a second. Helix angle, that's going to be the angle of the thread. Lead and pitch I need to explain in a second. Pitch, well, let me do the other things first. So roots down here at the bottom of the thread, crest is at the top. Depth of thread, thread angle. All right, so pitch is the distance for one thread on this. It's the distance from either this from here to here, from here to here. It's the distance, axial distance between the peaks here. So essentially that's your threads per inch. Lead. So for a single thread, the lead and the pitch are going to be the same. You can have multiple lead screws or double thread screws, but they're usually called the number of leads. So a one lead screw means that there's just one helix that wraps around this thing at whatever the pitch is. A two lead screw would have two separate helixes, so I'll be like one helix and then there'd be like another helix that would be shifted over. And so those things would have to have a lot lower pitch because essentially, like one lead would be here, 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 and here, and here. And then the other lead would be here, 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 here. So in this case, the lead would be twice. So the pitch would be twice. Wow, it's hard to explain. The pitch for each of these would be whatever this would be the pitch, because that would be, if you started on this, that would be the rate at which it would advance if you were turning it. And the lead would be, I don't know if this is right. I don't know if I believe that. The pitch would be for each one of these helixes. So the pitch would be for the pitch would be from there to there in a double lead screw. And then it just depends on how. I guess I've seen, the reason I'm kind of hesitant is I've seen it both, defined both ways, the pitch and lead. The pitch is the pitch of the actual helix itself. For a single thread, it's all the same. For a double thread, the pitch is going to be that, because that's how many threads per inch you're going to get if you turn this thing like on a lathe, on an engine lathe. If you put something in here and you turn this shaft one revolution, it's going to end up over here in a screw with two leads on it. But if you actually look and measure at this thing, you'll see that there will be a helix at this distance here, but one of them, this one, would be a totally separate helix that's been wrapped around it. So for a single thread, it's all the same, and it's easy. For a double thread, there's really two helixes that are offset by half the pitch. In a triple start screw or a triple lead screw, there's called starts. So a single start would be one helix. A double start would be two helixes that are offset by half the pitch. A 3-start would be 3 helixes that are offset by 1/3 of the pitch. So you see these in engine lathes on the lead screw. They'll usually have multiple starts. 4 is fairly common, and that's an issue whenever you're cutting threads. Outside of that, I don't know of a lot of applications for multiple lead screws. But the main thing to note when it comes to different starts and the different leads, for a single start, single lead screw, if I put something in here and I turn this thing, then this will travel all the way down and it will hit all of these locations here. For a double start screw, it's going to start here, it's going to go to 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 here, and I could put something else here and it's going to go to there, and it's going to go to there, it's going to go to there. But something that starts here will never end up there, because it's really 2 completely separate helixes that have been offset by half the pitch. So that's the difference between like different multiple starts, multiple leads. Again, probably just confused everybody, but the main thing is a single thread. It's just one continuous helix that wraps around that gets all of these points. In a double start or a double lead, then there's 2 separate helixes that are offset from each other, and something that starts in one of those helixes never gets to the other one. Essentially, this angle would be twice. This angle would be twice as steep. The helix angle would be twice as steep for each helix, and you have these 2 helixes that are nested within each other. So that's something that you have to pay attention to more when you start talking about lead screws. You'll buy them by however many starts they have. Again, they'll have a lot fewer threads per inch, and the helix angle will be a lot larger than you'd think it would be for those. And that's, for screws and fasteners and things like that, you're not going to see it. Usually for lead screws, it becomes more of an issue. Thread form, this is for the unified thread, where we've got our thread height, we've got our thread pitch, and we're going to define a whole lot of things based on that. We're going to define off how much we round this off. We're not going to have this sharp usually, just because it's going to be wear out. Sharp points on metal are going to get worn off into round points, so you might as well pre-round it. And when you machine the blank, you either machine it down to here, or when you forge it, you smush this material out of the way. Either way, you're going to round off the excess, or just make this flat. You're going to truncate the thread up here. Likewise, you really don't want to rely on this being down to a sharp point down there, because it's hard to machine, because you need a tool that's like got an infinitely small radius right there, and that's not going to work. So we're going to truncate the bottom of the thread a little bit too, and so the threads are going to engage. There's going to be some minimum point down here where the threads, so h/4 in this case, where we don't engage past that for unified threads. And you can see why this had to be standardized, because if you had something that was followed this profile, but then you're threading something on it that required to be down in this area, you're going to get interference and bad things. So that's why we had to standardize all this, is just so fasteners could be sold and interchanged. That would be external thread. For internal thread, same thing. So here's the workpiece up here. So you're going to truncate the thread here. So like if you did this on a lathe, you're going to bore the hole out to this dimension, and then you're going to machine out this part here. You're not going to machine down to the corner here, just because there's no practical way to do sharp corners like that. The tool's going to have some radius on it, and if it doesn't, it will have a radius after you start machining with it for a while. So there's different clearances for these when you get into different kind of fit classes for threads. So you have to watch metric threads, ISO threads, a little bit different definitions here, but same basic process, where we truncate the top and bottom of the threads a little bit here, and we just basically rely on some portion of the thread here, and not the full portion of the thread. So these are something you could look up in machinist handbooks. There's the machinist handbook that's about, I don't know, a few thousand pages. It's very, very thick little book that has kind of got all of the calculations on this. If you were going to try to cut threads by hand, we'll talk about in a bit, but thread cutting by hand is sort of a giant pain, and you really do need some kind of a cheat sheet for cutting them. Make sure that you get these truncations in the right spot, and you're using the right tooling to do it. Power transmission threads, Acme's fairly common. It's a trapezoidal profile here with the characteristics shown. Buttress thread, for driving mainly in one direction. Acme thread you can drive in both directions. Buttress thread would primarily be for driving in one direction. You see square thread to you see Acme, you see square. I haven't seen a lot of buttress thread, but Acme thread's pretty common. Square thread's pretty common. Here's the 29-degree worm thread. I'm not sure of anything that's pretty close to Acme. You can see it's a little bit different, so that's something that if you didn't measure, you might confuse Acme and worm thread here. But Acme is fairly standard for power transmission. Square thread you see too, but again, buttress thread's pretty rare. I would say I haven't seen it anywhere. Pipe thread, that is a tapered thread. So here it's 3/4 of an inch per foot taper to the threads. So that kind of makes it interesting to make these threads. But usually you don't have to be super precise with how deep you go on this thing, because you just keep, since it's tapered, as long as you've got enough thread on the taper, you just keep turning it in until it gets tight. So pipe thread, that's the deal with it, is to seal it, you just keep turning it in until essentially, this is going to go into a cone, and you just keep twisting it in until the cones touch and it gets tight and it stops leaking. To get enough, you usually need some kind of lubrication to get the threads to engage enough to seal, and that's what this Teflon tape is all about. So you really only need Teflon tape on tapered threads. There's a few other applications where you might want it, but straight threads, it doesn't really do anything. It's usually not the seal on straight threads. On these, this is the sealing portion. It seals on this plug, so you really need that to be tightened a lot. In that case, you need something to lubricate it. That's what the Teflon tape does. So you wrap the Teflon tape around it, and you turn the part in, and you turn it until it stops leaking. If it leaks, you turn it a little more. If it keeps leaking, you back it off, put more Teflon tape, and tighten it again. And eventually it stops leaking in most cases. That's sort of the deal with tapered threads, is you just tighten them until they stop leaking or you break something. That's just how they're designed. There's other methods of sealing pipes where you've got straight threads, and then you'll have sort of a taper down here, and then you'll have on the other side, you'll have some kind of another taper, and it will seal on these tapers. So like AN fittings, that's how they seal, and it's usually a nicer sealing method. You don't have to crank down on things as hard, and you don't have to use Teflon tape at all, because the sealing is all on this taper here. You can still damage the fittings on it, but usually they come apart easier and go back together easier, and if they're done right, they don't leak. There's O-ring seals too, where you'd have straight threads in an O-ring seal, and those wouldn't require a lot of torque. But the main reason they use these on pipes, like in plumbing applications, they're cheap. They're easy to do in the field. You can tap these things in the field, and you can get fittings that already have the taper on it, and you can get just a blank steel pipe, and with a threading, a die machine, a thread cutting machine, you can cut the tapered threads on it, and then just with a pipe wrench, tighten some Teflon tape, tighten these things up. I'm not sure of metric tapered thread standards. I'm just familiar with American pipe thread. So there'll be a pitch on these things, like threads per inch. There'll be a diameter, and then it'll be NPT. Usually is what you'll see on that. So an NPT is a pipe thread. 4 main ways of making threads. You can cut them, you can machine them. You get good machining accuracies on them. You can cut tapered threads. You can cut basically any kind of thread you need. You can grind threads in really hard materials. You can roll threads if you need to make a lot of something. That's more of a forging process, and there's a lot of advantages in this. It's cheap and at volume, and you get forged threads instead of cut threads, so it'll be generally a little bit stronger. And in some applications, you might be able to cast them or 3D print them in place. So external cutting of threads, you can do that with a die. It can be a manual process. Again, there's some power die thread making machines for like iron pipes or something in the field. They make these big machines that you can put a big piece of black iron pipe in, and it'll run a die down it. And because just doing that by hand on like an inch or 2-inch steel pipe would be a nightmare, or even a bigger pipe. This 13 to 16ths, I don't buy that. You can get dies down to 1/4 of an inch or so. The smaller things get, the more of a pain it usually ends up being to some point. But Yeah, the dies can get fairly small. It's hard to get these things started. They really need to be perpendicular to the surface that you're machining. If you start these things at an angle, it's not going to fix itself. It usually just ends up crapping out the threads and then not working. So it'll just bind up and not work. So you need to make sure that this is perpendicular to the axis of whatever it is you're trying to cut threads on. I really don't like cutting threads with dies, but sometimes you have to. For harder materials, for stronger steels, for stainless steels, thread cutting can be a giant pain. So in a lot of that cases, it'd be nice if you could buy a fastener that already has threads, or maybe machine something on a lathe. That works a lot better than die cutting threads. I try to avoid die cutting threads if at all possible, because again, it's a massive pain to do. There's these for external threads. There's these lathe self-opening die heads. I've never used one of these things, but if you're going to do a lot of external threading on a lathe, these are really nice. Where you basically get this thing started with the quill, it automatically feeds in, cuts the threads, it gets to the bottom, and then it pops these teeth out, retracts, and so you don't bottom things out. I've never used one before, but if you're cutting a lot of external threads on a lathe, that would be really handy. A few different kinds of those. I've seen these before. I've just never used one before. You can also single point with a single point external threads on a lathe. So here you've got a tool that's got the angle on it, the thread angle there. The problem with doing external threads on a lathe is you usually can't do these in one pass. You usually can't machine full depth, so you've got to make several smaller passes down to the base of the thread, and the lead screw usually has multiple starts in it. So what that means is you have to make sure at each sequential pass, at each depth, you have to make sure you're on the same start on the lead screw. And there'll usually be this little rotary dial that will have different indicators on it, like 1, 2, 3, 4, and there'll be some stationary thing, and this thing will spin at some keyed to the velocity or the angular velocity of the lead screw, and there'll be some kind of a clutch. And so if you start this first pass with start 1, you're going to machine down to here. You're going to disengage your power feed, or you're disengage the clutch. You're going to move this thing back out and then get down to the next depth, and then you need to re-engage. It's the half nut, what that's usually called, but you need to re-engage this clutch when it gets back to the start at 1. If you engage at one of the other starts, it's going to machine phased off, and it completely ruins your threads, and you've got to start over again. There's a little bit of an art to it. Once you get it figured out, it works okay. I hate doing it. I prefer to not cut threads at all if I have to. There's just always a pain, and it's one of those things that if you do a lot of it, you get good at it, but if you have to do it every once in a while, you end up having to do several test parts and scrap stuff. It's just a massive pain. You always have to run for really low pitches where this is feeding quite fast for the RPM. You've got to watch crashing this thing on the chuck. I've done that before doing a powder lead screw that had a really low threads per inch, and even at really low, like 20 or 30 RPM or whatever the minimum RPM of the spindle was, this thing was still moving super fast and just crashed the hell out of a lathe. It was okay, and I was okay, but it was not pleasant. So yeah, external thread cutting, it's one of those things that once you get used to, it's fine. You need a little bit of clearance here because you're never going to stop this thing right at the bottom here. You always need a little bit of a clearance room, and you need to usually turn the lathe pretty slow. My preference is to use a CNC lathe for any kind of thread cutting. A lot of these can be done with N and G codes. M and G codes. Usually G codes. G codes, they'll be for different machines, different can cycles for cutting threads, and lathes will do a fantastic job of it. You don't have to worry about that start situation at all because it uses a servo instead of a lead screw. Cutting threads, internal or external, on a CNC lathe is a breeze, and I love doing it compared to trying to do stuff on a manual lathe. Internal threads, taps work until you break a tap, but they work much better than dies do anyway. So a die external threading is a pain unless you've got a CNC lathe that can cut threads. Internal is really not bad. Different kinds of taps. These would be just kind of a hand tap here, where they've got the standard little square chucking area where you can chuck them up into a tap handle. And then there's three main types: tapered, plug, and bottoming. So you usually get started with a tapered or a plug. Plug is pretty common for taps. You pretty well, for smaller taps, you usually buy a set of plug taps, and then you'll need the occasional bottoming tap for a blind hole that's not through and you need to get threads all the way to the bottom or as close to the bottom as you can. This has got a lot of taper on it to help you get started. Trying to start one of these, it's not going to happen. You're not going to start tapping a hole with a bottoming tap. It's got to be lined up perfectly. It's going to be really hard to get it started correctly. So you're almost always, if you need threads all the way to the bottom of a hole, you're going to start with one of these that starts easily, and then you're going to switch over to a bottoming tap if you need threads at the bottom. It's almost always better if you've got a through hole. If you're going to tap it, sometimes you don't have the option and you got to have a blind hole. But if you've got a through hole, chip's clear, and you can use one of these for the whole thing as long as you have enough thread on it. Internal threading's a little bit of an art to this too. You're gonna need, I think, is there an advanced slide on this? Yeah, there's a couple more comments on it, but what I'll say, doing this, breaking the chip is really important on this. If you just try to cram one of these things in for smaller taps and harder materials, it's very easy to break a tap. And these are made out of high-speed steel, or really high carbon steels, and they're really strong. Usually a lot harder and stronger than whatever, and a little more brittle than whatever material you're trying to tap. And if you break a tap off in, it can be very difficult, if not impossible, to remove it. Because you really, these things are brittle, and so when you try to get them out, they'll usually break into pieces instead of just coming out intact. You can't really machine it with anything because it's the same material that your machining tools are made out of. There's some weird ways of doing it. You can plunge EDM out, almost all of it, and then pick the threads out with a pick. In emergency applications of expensive things, I've seen that where you can plunge EDM. This is like, you've created a huge problem that's expensive to fix. But it's cheaper to plunge EDM that out and pick the threads out than it is to replace whatever expensive part you broke a tap off in. You got to do what you got to do. But the main thing is to not break taps. So when it comes to purchasing taps, buy good taps. That's one thing you just don't, external lathe cutting tools, buy nice stuff, but the cheap stuff, if it breaks, it's usually not a tragedy. Taps, when they break, is almost always a tragedy. So you don't want your taps to break. So buy nice taps. When they get dull, buy a new nice tap. You really can't sharpen these things because I don't know any way you would be able to sharpen these things. Maybe you could sharpen the point on some of the first few threads and make the whole thing shorter, but I've never done that or seen it done. But yeah, buy nice taps, and when they get dull, replace them. You have to use some kind of a cutting oil in almost all cases on this, and usually a specialty cutting oil like Tap Magic. In fact, I don't know anyone that doesn't use Tap Magic that's a machinist. Every machine shop I've ever been in, you've got aluminum Tap Magic and regular Tap Magic. And for aluminum threads, you always use aluminum Tap Magic. And for steel, you always use regular Tap Magic. And I'm not a salesman for Tap Magic, but I've never seen a machine shop that used anything else for that. Just regular cutting oil, people just don't seem to use. So there's probably a reason for that. And it's probably because it works. They make small to large. At some point in time, this is pretty safe operation. Usually once you start getting past 1/4 to 5/16 taps, it's pretty reliable and you don't break them. When you're trying to tap small, like a 1032 hole in something really hard like 4340 steel or some stainless steels that work hard and bad, this can be a nightmare. And the main thing is to not side load the tap. If you're loading it purely, putting a pure torque on it, you can still break them. And it's usually because you haven't broken the chips or you're just working too aggressively. A lot of times if you're tapping these by hand, you'll side load this thing and just snap it, especially for the thinner taps. So you need to make sure you're not side loading. You can do this in a lathe where you're holding the part in a chuck and lock the spindle down so it won't spin. And then use the tailstock. These will usually have, your tap handle will usually have a centering hole in it that you can put a dead center or a live center on and keep these things straight, at least for the start, if not to finish the whole operation. You can do this in a mill too, where you use the quill to get these things started. I've seen some old pro machinists that We'll tap holes all by turning the mill on with a tap in it, turning it off, and then pulling the coil into and start the threads, and then just using the inertia of the mill to continue to tap through, and then they might bump the motor on a couple times and then reverse it to back it out. I've always been too scared to do that because usually I'm machining something that I don't want to mess up, and I've got time to do it. But you know, those guys are in a hurry and got other things to work on, so they use tricks like that. But that might be fun to practice, but on stuff you don't care about until you've got it figured out. There's some fancier taps too, some spiral taps for CNC machines that you can, like in these, I really don't like using these in a CNC machine. The spiral ones, they clear chips better, and they seem to work better in CNC applications. These are good for hand applications. You can single cut internal threads for big applications. You know, for really small, like a 1/4 inch, there's no reason to single point that. You could, but I don't see why you would want to. These things come in sets, tap and die sets. I haven't found one tap and die set that was worth buying. You get a whole set like this, and you get a bunch of different things, and unless you spend an absolute fortune on this, it's going to be pretty crappy. So, I mean, a good tap and die set would be, like at least $500 or $600, I'd have to think, for something that's actually worth using. You can buy cheap ones at the hardware store. They're garbage. They're just universally garbage. The handles like this, you just basically, I want to throw away. They don't hardly work. This I don't know who makes this. This might be a decent one. I don't know. It doesn't look decent to me though. I really like using this style of tap handle. And I like using good ones. Starrett makes really good tap handles for that. These style, after you've got threads started and you need a little bit extra torque, they work, but you need to buy good ones because the bad ones like this end up causing more trouble and breaking taps. When it comes to die handles, I've not run into a good die handle ever. So the ones like this, the set screw doesn't engage right, or something wears out and it stops holding on to the dies. Just not ever had good luck. You can start these things with sockets sometimes. Sometimes that works, and then you can use a socket wrench to drive these down after it's started. That works as long as you get deep well sockets, and that's going to be a nice socket wrench is going to be better than one of these crummy handles like this. You're going to get what you pay for when it comes to taps and dies. So what I recommend is buy a really nice set of taps with the screws, the bits that come with them, because you're always going to end up breaking those bits out of your drill index if you don't buy bits with your taps for the common sizes, and then maybe buy a set of dies for the common sizes, and then just buy handles, tap handles and die handles. Spend good money on those because you're going to be reusing them. Buy nice taps and dies, but plan on replacing them at some point in time. Don't buy some gigantic set, because usually you want to buy the ones you need. You're going to use like 1/4 28 and 1/4 20 you're going to use all the time. 1/2 13 you're going to use all the time. Well, a good chunk of the time. 1/2 20 maybe. There's some goofball sizes that you're just not ever going to use. So having a big set, I don't know, unless it's really good quality, it's kind of a waste of money. Because what you'll see in tap sets that have been used for a long period of time is like the 1/4 28 will be missing or broken, and then there'll be a bunch of oddball sizes that you're never going to use that we'll never use. So it's better to just have the common stuff and be prepared to replace it, and not have spend a bunch of money on the things you're never going to use. Anyway, rant over on tap and die sets. Cutting fluid used extensively for all applications. Don't tap without using a cutting fluid. But maybe plastic, but even aluminum, you're going to want to use some sort of cutting fluid. And again, Tap Magic is the gold standard for that. I just don't see anything else used. So, and there's got to be a reason for that. I mean, it's got to be because it works. So, again, I highly recommend buying a small set of really high quality taps for the common sizes. It's got somewhere around like 10, 24. Really, you need 10, 24, 10, 32, 1/4 20, and 1/4 28, and then the few sizes above that probably up to 1/2 13 and 1/2 20. Those sizes from 10 to 1/2 inch. Buy a set that's got those in it. that's a really good quality set, and that set will cost you, I don't know, 150 bucks probably. I can't remember what my set costs on that. I usually don't like buying nitrided taps because they end up, they're going to wear out and need to be replaced at some point in time. So a really good quality high-speed steel set, something that's U.S. or German or Japanese made, it's what I highly recommend for taps, because the risk of them breaking is usually a lot more than, oh, I spent a little extra money. And so yeah, buy nice taps. Dies, I've never bought a die set I liked, so I have no input on that. Don't use dies unless you have to. That's sort of my advice on dies, but sometimes you have to. But if you can cut them in a lathe, it's going to be easier. External thread milling in a CNC mill, you can do multi-point thread milling, where you've got a little cutter like this, you spin it, you move it in a helix, and can machine threads fairly quickly. Again, this will be done with some kind of CAN G code. It'll be machine specific whether it can do it, and if so, how you set it up to do it. But for CNC machining external and internal threads in a mill, this works nicely. Never done it personally. Seen it done. Never done it. Again, I'll link the videos. Grinding for some really hard materials where you need precise threads. That might be an attractive way of doing it. Similar process to cutting on a lathe, except you're going to use a spinning grinding wheel. So it works like single point threading, but you're going to use a rotating thread shaped grinding wheel, and you're going to have to move it, feed it in axially as the part turns radially. There's center type, there's centerless, so this would be center type here. There's centerless, where you've got two wheels, just like centerless grinding, and that can produce set screws, the screws that don't have a head on them. There's also rolling, this forging threads essentially, where you've got a die and a workpiece. You smush these things together, and so what's going to happen is you're going to smush some of the material up, some of the material down. So the major diameter of this ends up actually being larger than the original diameter of the stock. You're forging the threads so that they're going to be stronger. There's no chips. You get a really smooth, hard surface. It's a really nice process. You just need the equipment to do it, and need to be machining threads forging threads that this works on. So when you're machining, you have your bar diameter at whatever this truncated top diameter of the threads are, and then you remove this excess material here. In forging threads, rolling threads, you're going to smush some material up, some material down. And so if you find a fastener or something where the threads are larger than the shank diameter here, that's probably because they were forged into shape. In machining, you could always machine this down here at some point in time. You could always machine something that looks like this, and then just cut the threads here and have them be bigger too. But in general, when the threads are bigger than the shank, it's because it was forged. Grain structure is going to be better in rolled threads, right? You're going to have here, the grains are going to stop right at the end, and that's going to be where your cracks form. Having said that, how often do you break threads out of things? In some materials that work hard, like aluminum, that aren't very strong, you can pull threads out of it. And steels, it can be pretty hard, but usually machine threads work fine as long as you take care of them. The forged threads usually just stand up to repeated tightening cycles better, and or just a little bit stronger. But it's more about cycles than the initial torque in on something. It's more the loosening and then retightening cycles. There's flat die sets where you got a stationary die and a moving die, and you put the part in there and it mushes the threads into it. Obviously you need a very rigid machine for this, and these dies are going to be very expensive. Centerless here, obviously this is going to be very expensive. These dies and the machine itself are going to be expensive. Same thing like centerless grinding. You've got two wheels. One of them is going to be skewed. That causes the infeed. And so for like all thread, this is how all thread's going to be made in probably most all applications. Yeah, I just don't know why you'd cut it. The centerless roller like this for any material that's ductile enough to be rolled. This is going to be the way to make all thread or set screws. Planetary sets, too. It's how it's made video. I remember seeing this just watching TV one day. I saw this video, and they had a big Planetary thread rolling machine like this. Expensive, right? This is an expensive piece of metal. This is too, but you're going to make a lot of fasteners with it. Chipless tapping, I've never seen this before, where you're basically forging internal threads. So obviously this thing needs to be incredibly hard. It's made out of high-speed steel. That limits what you can. You're basically just mushing threads in internal threads. So you're cold forging internal threads, fairly small diameter, no chips because it's a forging process. Hole diameter needs to be very precisely controlled. You're talking about ductile materials. This might work for aluminum. I imagine you're going to break a lot of these trying to figure out. Yeah, you're going to need some kind of cutting oil for this. I guarantee it. I've never seen this done, so I can't provide any input on whether it works or not. But for some softer materials, it might work pretty well. Casting in place. You'll see that in some applications, like drink bottles, the threads will be cast in place. 3D printing threads, it works kind of, but they're usually terrible. 3D printing does not lend itself to making threads. Some fittings like this, they might be cast into place. I would be surprised if these threads were bolt cast in place. They're still probably going to need to be cleaned up afterward. And you can see the surface finish here. That's not an acceptable surface finish for threading. Thread maintenance. Threads can be repaired, thankfully. So if you bust the threads out of something expensive like an engine block, like a head bolt, and you bust the threads out, it can be fixed. So the usual process for fixing threads is to bore the hole out to a larger size, and then use some kind of an insert like a helicoil, where you tap a larger threaded portion and then you screw in one of these little hard steel coils, and that creates threads back at the original size on the inside. And for like aluminum, the helicoil is going to end up being stronger than the original aluminum was, so it ends up being better than it started if you do it right. So as long as you've got room to drill a bigger hole and get a helicoil in there, it solves the problem. Helicoil is a trade name. There's other methods of doing this too. I've used a few of these, whenever you pop threads out of something expensive, like usually an engine or something like that. It's an option for fixing. You might even do, like on an aluminum part, where you really need to torque something down a lot. You might do this from a new part from the factory. You might put some kind of a thread insert in, just so you've got nice, strong, reliable steel threads. This usually comes kind of a specialty thread profile for these. So you usually buy sets basically for fixing there'll be a set for fixing a 3/8 hole that'll have the drill size, the die. The drill size, the tap, and it'll also have the coils that go in. There might be some feature for keeping these things from rotating in the hole, for non-blind holes, for through holes. There might be some little tang that you can kind of crimp into place and keep these things from rotating. Thread compounds, in a lot of applications, again, especially high performance applications, you might use some kind of a thread compound to make sure that the torque spec is correct. Because if you're thinking about when you're torquing the head of a bolt into a thread, and you're trying to torque it to a specific torque spec in foot-pounds or Newton meters, if there's a lot of friction, then a lot of the torque is just going into overcoming friction and not actually stretching the bolt, which is really what you're trying to do with the torque, is to stretch the bolt a specific amount. And if all of your torque or a lot of your torque is going into friction and not into stretch, then you have no idea what the final stretch is of the bolt. So if you use some kind of a lubricant, that reduces the friction, and then you're more likely to get your torque into stretching the bolt and not into friction. In really, really critical applications like connecting rod bolts, you might actually measure the stretch of the bolt, the deflection of the bolt, with some kind of dial indicator to guarantee that you've got a specific amount of stretch, especially in torque to yield fasteners, where you torque a fastener to the point where it stretches and permanently deforms, it plastically deforms. That's one way of guaranteeing a clamping load in very critical applications. You see a lot of cylinder head bolts nowadays, some rod bolts or torque to yield bolts, and they have to be stretched a very specific amount. And those you might torque them to a spec and then turn them a specific amount, like 90 degrees or something like that. Or get a dial indicator out and actually measure the stretch for bolts that you can, like rod bolts. There's fixing compounds for preventing these things from coming loose. That's usually in blind applications, where you screw something into a blind hole or even a through hole, where you put a screw into it, not a bolt. you might use a Loctite or some other thread. What's the word I'm looking for? Some kind of thread locking compound on a nut, but usually it's on a screw, where you screw something into something, and there's no way of preventing it from backing out. If you need to prevent a nut from coming loose, you want to use some kind of a metal lock nut or a nylock, some kind of positive locking feature, a castellated nut, something like that. The Loctite comes in, the other thread locking compounds, when you're tightening a screw into something, and you don't want to use safety wire to keep it from backing out. So there's all sorts of different Loctites. There's the blue type, which is usually you can take it apart with hand tools. Then there's the red type, which it starts to become a problem to back this out. In this case, this is the breakaway and prevailing torque. So here it takes 17 Newton meters to break this thing away, and then it will require continuously 6.8 Newton meters to keep backing the fastener out. For the red here, you'll see that it takes 31 Newton meters to break this thing loose, and then it continuously takes 31 Newton meters. So there's no drop off once it breaks free, and it'll really prevent the fasteners from backing out. And the problem with most threads is once they're loose, and there's something that vibrates and shakes. It just continues to loosen. That's why the thread locking compound comes in. It prevents it from starting to back out. These prevent it from starting to back out. These prevent it from starting to back out, and then they'll continuously resist the fastener from backing out. These you don't want to take apart unless you have to, and you might need to put some heat on it. Heat will break. These are going to be organic compounds, so some heat's going to need to be necessary to break those things down to get fasteners out. You can see the prevailing torque here lasts for 180 degrees in these cases. All metal, like in a bolt and nut application, an all metal lock nut's going to be better because the prevailing torque is always going to be there until you get to the very end of the threads. Again, there's some applications where you need to screw a screw into something and you really can't put an all metal lock nut on it, and you might need to use some kind of a thread locking compound like this. Alright, so that's it for today. Thank you all. I'll get the next quiz posted on Canvas. That's it. Thank you.